Right, it's 10 o'clock, so I'm going to make a start and welcome you all to the 2021 CIBSE Technical Symposium. Thank you for joining us. I'd like to thank everyone who's joined and also everybody who's contributed to making the event possible. There's a large number of people who contribute to the symposium. Thank you all. This morning, we're going to be welcomed by CIBSE President Kevin Kelly in a few moments. And we're also going to have a few words from Franz Hule, who represents Rehau, one of our sponsors. And before we move on, I'd like to thank all of our sponsors. I know it's a cliche to say that without our sponsors, this wouldn't be possible, but it is absolutely true that we do need our sponsors. And so I hope you will support them through the app and see what they have to offer in the course of the symposium. So without further ado, I'd like to introduce Kevin Kelly. Kevin is CIBSE President for this year. He took office in May, and he's now going to say a few words of welcome to us. So good morning, Kevin.
Thank you, Hal. And I'll just try and share my screen. I can. And so, welcome to the 11th Annual Technical Symposium. This is the second time we've been online following last year. And you will see some of the happy people who were gathered at the end of last year's symposium. I'm not quite sure why they're so happy, whether it was because the symposium was over or it was because of all of the new knowledge they gained, but I'm sure it was the latter. This is the second and hopefully last to be virtual. And whilst opportunity to attend might be easier online, we do miss the social interacting and networking. Next year, maybe. I have been attending these symposia for many years and also presented and acted as reviewer. So I know how much work goes on behind the scenes in preparing for an event like this. In particular, I would like to thank all the authors and presenters, over 60 of them, for sharing their work with us. All the reviewers who quietly worked in the background to provide constructive feedback, and all of the CIBSE staff who worked tirelessly in making this event happen. I also want to thank all of our sponsors for this year's event. Without any of the above people, this event would not be possible. My friends, over the next 2 days, you will see a wonderful and diverse group of presenters who will try and close the performance gap by disseminating their research findings and help to take the mystery out of research. We strive for perfection in our work, but never achieve it. Instead, we get as near as we can, measure the gap, and figure out how to close it. We share this knowledge about successes and indeed failures to help inform our colleagues in the profession. We learn from successes and failures. However, those who fail to evaluate their innovations or who fail to share and disseminate their findings are missing more than a trick. It is by collaborating we get nearer and nearer to closing the gap. So research in our profession is an iterative, inclusive process where we share our findings. If you as a working engineer struggle to produce research findings, then consider collaborating with an academic colleague. Practitioners are data rich, whether they realize it or not, and academics are often data poor, but expert in research writing. Over the next 2 days, you will see papers on topical issues such as indoor air quality, ventilation, and the challenges of delivering safe, healthy, and energy-efficient indoor environments. There are also interesting topics such as sustainable lighting and weather data for building design, resilience, effective heat sourcing, and the energy performance. We welcome several papers from overseas authors, highlighting the challenges of sustainable retrofitting of buildings, and of course, for those closer to home, looking at how to achieve low carbon refurbishment in the UK. publishing a research. To all of those involved today, I would encourage you to consider submitting research to a peer research journal. CIBSE has two, which provide a wealth of knowledge and information to support engineering practitioners. Finally, to our program. The on-session demands were available from Tuesday last week, and the live sessions over the next 2 days will offer a chance to ask questions of the authors and provide opportunity for a live discussion about the issues raised. I welcome you all warmly to the CIBSE Technical Symposium 2021, Engineering the Built Environment for a New Normal, Delivering Safe, Healthy and Versatile Buildings. And now I hand over to our gold sponsor, Franz Huel from Rehau.
Thank you, Kevin. Good morning, everyone. My name is Franz Huel. I'm the head of technical for Rehau's Building Services Division in the UK and the Nordics. And it's a great privilege to be the gold sponsor of this event. Firstly, I wanted to talk a little bit about Rehau because I think and fear that not many of you actually know what we are doing. We are still a privately owned company, despite the fact of the size that we are. And as a family-owned business, we have a very strong focus on sustainability, on looking ahead of the responsibilities for future generations. We look at very intently at closed value chains that start from design all the way through to recycling. And if you would go to the next slide, you'll see what we have in terms of products that I'm going to talk about briefly now. Rehau has been recently elected into a UN initiative called 50 Global Leaders of Sustainability and Climate Change. And it's a recognition of our continuous commitment to making things last long and getting a really long service life out of the systems. So if anything piques your interest of what I'm talking about in the next few minutes, then please do get into contact with us, either by phone or email, or even meet us. We're happy to meet these days again, which is really nice over a cup of coffee. It makes all the difference, and you can explain so much more as well. We are in the UK the leader in polymer district heating systems, which you see in the top left. Those are flexible pipe systems that are predominantly used in fourth generation heat networks, considerably contributing to lowering the decarbonization of the heat network in the UK, of heating. We are also the only flexible district heating pipe manufacturer in the UK. We have local production. Therefore, we have a lot lower CO2 emissions with transporting of the pipes to site. On the top right, you see a floor heating system that we developed specifically for the multi-occupancy project and multi-occupancy market. It basically allows reduction of screed and the reduction of the concrete needed in a building, thereby reducing the embodied carbon quite considerably of multi-occupancy building. It also uses, of course, underfloor heating to distribute the energy and the heat into the building, thereby potentially even further reducing the operational carbon of the building, while at the same time providing a really good, if not exceedingly well, acoustic performance. On the bottom left, you see our recently launched smart control unit. The smart controls are based on a very, very flexible hardware platform, which allows us in many years to come to roll out new features via over-the-air updates simply by changing and adding to the software without having a need to change the hardware or adding new hardware components to the system. We only recently this year launched and added the cooling functionality to the system and fan coil integrations. So this system at the moment already can control multiple heating and cooling systems all from one control unit. So there's no need for multiple controls for each individual systems anymore. You can have everything out of one central point. On the bottom right, you see our plumbing offering. So you see our acoustic soil and waste pipe, which is the white large pipe, which when you compare it and all the impact categories that we have on an EPD versus ductile iron or cast iron systems, you will see that we score a lot better on each of those individual impact categories, while still providing a really good, if not superior, acoustic performance over ductile iron. Even if the ductile iron system, by the way, contains 80% recycled, we are still a lot better on each of the impact categories. And then on the very bottom right, you see our MLCP polymer hot and cold supply pipework, which I will go into more detail on the next slide. If you could have the next slide, please. When you look at plumbing systems, we are all aware of the risk of dead legs and what they actually cause in terms of water hygiene and water quality. So we are all normally quite attuned to what to do and how to avoid them. But my pleas or my little point of discussion is, have you thought about the micro dead legs that exist in those systems? And when we see the next slide, you actually can understand what I'm on about. There are jointing systems, pipe jointing systems, which do have little pockets inside the joints areas themselves, which trap water. And trapped water is always an issue, as we all know, because whether it's a large dead leg or a small dead leg, you only need a small pocket for bacteria to grow. But there are also jointing systems like the one you see on the right, which is our Everlock compression sleeve joint, that doesn't have those pockets where water can be trapped, and thereby aiding and supporting a clean water. We also have, as a company, decided a couple of, well, actually a year ago, to change all our metal alloys over to a lead-free gunmetal. That's an alloy that we developed ourselves over 7 years together with a partner in Germany. And that basically brings together the best out of both worlds. One from the gunmetal side, which means it's highly corrosion resistant, regardless of the water aggressivity. And it's also the best for hygiene because it doesn't leach any lead into the water like DZR brass usually does. When you look at the EPD side of things and the impact categories, it may surprise you that the polymer pipe system actually scores a 3 times lower global warming potential and up to 4 times lower ozone depletion layer potential than comparable copper piping systems. Even if the copper piping systems use recycled material of up to 80%. So if there's any interest in more on those EPDs, we have them, they're independently verified, and they're always based on cradle to grave and for a full installation, including fittings and pipe, not only a pipe or cradle to grave, cradle to gate. So this is something to look out for on EPDs. And then last but not least, on the last slide, I just want to draw your attention to what we call thermally activated building systems, or TABs, which are increasingly used in BREEAM excellence buildings or passive house. And you have PEX-A pipes that are being embedded into the concrete structure themselves, and you activate them with hot water or cold water to heat or cool, and they significantly reduce the OPEX and the CAPEX. So on the next slide, you will see some figures of those systems, together with the fact that we are introducing and writing a technical article into the CIBSE journal next month, and also working on a white paper that we will launch in August on this system to actually stimulate the discussion and the uptake in the UK of those systems. BREEAM has been involved in several systems in the UK, from university to office buildings, but on a global scale for the last 20 years, BREEAM has been involved in over 400 projects of this system, and we installed more than 2 million square meters. So we know what we're doing. It's a really well-designed system that brings a lot of benefit to the building. And with the new ways of reducing the concrete used in buildings like bubble decks, or the new hybrid systems of timber and concrete together, the system still performs admirable and brings all the benefits to it as originally. So that's it, a a short snapshot of REHAU. Thank you very much for allowing me to do so. If you have any questions, as I said earlier, please get into contact with us. And I do hope that the next 2 days will broaden your horizon, will bring you new ideas of how to move forward with making this world more sustainable and safeguard it for the future generations. Thank you very much for allowing me to speak, and I wish you a really good 2 days. Thank you very much.
Thank you very much, Franz. And what I'd like to do now, without any further ado, is to, I'm trying to get to the next slide, is to introduce Professor Kath Noakes. I can't get to the introduction slide, so I'm just going to stop sharing. And Kath is known to many CIBSE journal readers for her work on ventilation, and she's become very well known during the past year and a bit because of her work on ventilation in response to COVID. And that's what Kath's going to talk to us about now. So without further ado, thank you, Kath, for joining us, and over to you.
Okay, thank you very much, and thank you for inviting me to speak today. So I thought, I mean, we've had an unprecedented 18 months or so for all of us. And thinking, when Harold asked me to speak at this, I sort of took a step back and thought, what can I think about today? And I think it is time to start thinking about going forward and how we learn the lessons from some of the things that we have learned over the past year. So that's where I'm going to focus on today and start to think about the future. I'm going to start though with a bit of past, which is the burden of respiratory disease, and the fact that, I mean, these are data from 2016, it's worldwide data from WHO, but we can see that respiratory disease sits very significantly in the top 10 causes of deaths in the world. Some of that is diseases associated with poor air quality, including heart diseases and strokes, as well as things like COPD. But respiratory infections land very firmly high up there. Now, a lot of this burden is in lower to middle income countries, but we get an awful lot of these same diseases in the UK, and really our built environment has a big part to play in the management of these diseases. If we look at COVID itself, the figures are astonishing. Now, we've got over 185 million cases and sadly 4 million deaths worldwide. And there seems to be no reduction in this. It is still going strong worldwide, very sadly. And I think if we look at the economic cost of this, it's been estimated that the global harm of COVID is $1 trillion a month, which is a staggering figure. If you thought about the built environment, even if the built environment only tackled 1% of that, that would be a huge number in itself. So I think it just to sort of set the context of really where we are at the moment in terms of dealing with disease and the environments that we're in. If we want to think though about our environments, the first step we need to do is think about how diseases transmit. We're talking predominantly here about respiratory diseases. So here we've got a source of our infection. Usually it will be a respiratory source, but there are plenty of other infections out there, including very well-known ones such as Legionella, which might have an environmental source. The thing which actually distinguishes many of these is that they are introduced into the environment in the form of droplets and aerosols. Those come from a particular location, a person or an object or a thing in the environment, and they're released at a particular duration of time with a particular force and a particular size distribution of particles. And we have to remember that although things like viruses are very small, they're maybe 100 nanometers in diameter, they are not naked, they're not there on their own, they're contained within larger respiratory droplets, and they don't evaporate to just become a naked virus because they're surrounded by things like proteins and salts and actually other viruses and bacteria. So they retained a whole range of droplet sizes from about just under a micron up to about 100 microns or even bigger in some cases. Once these are released into the environment, they get transported by the environment, they get deposited. And that is complex. It depends on the ventilation, it depends on people's interactions, it depends on the force with which they're ejected into that space. And then if they deposit, it depends on the surfaces and the cleaning of those surfaces. And ultimately, we can be exposed to those pathogens. So we can be exposed through inhalation, which we know now for COVID is probably the primary route. That's a whole range of different droplet sizes and aerosol sizes at short range, and then the smallest ones only once you get to long range beyond about 2 meters in a room. We also know that those larger droplets can be deposited directly onto people's mucous membranes, or they can deposit onto surfaces, or we come on fomites sometimes, to cause infection via that way. The other thing we know is that people who are infected tend to have contaminated hands, they contaminate surfaces, and that is another potential route of infection. But this whole process is really complex, and I think we shouldn't pretend it isn't. We have to consider what the microorganism is. You know, for COVID, we're looking at the SARS-CoV-2 virus, but if we're looking at Legionella, it behaves very differently. We're looking at the way people behave in that environment. We're looking at how that environment's designed and its systems. And then actually a huge amount of this is the fluid dynamics of what happens in this process from A to B. And from a medical perspective, clinicians often think about who's infected. They might think about the source. They think about what happens when people get exposed. They don't tend to think about the bit in the middle. And that's where the built environment comes in. And that's where we all come in. Let's just get my slides to work. Okay, so how do we know about transmission? It's not straightforward. There's a lot of different data out there, and it's all imperfect. And I think that's really important to say. So I've listed 2 groups of studies in that slide, which we can use. So the first set, the top set, which are in blue, are all the ones which relate to data around outbreaks, around the virus in the population, about where we can actually try and get data from the real world settings to understand risk factors, to understand the types of environment where people get infected, to understand who it's spreading in the population, to understand how it's spreading in the population. But that's quite high level. It doesn't tell us the mechanisms for what really happens. So then we need a whole set of more laboratory and modeling based studies where we can use, for example, animal models, we can use virology studies, we can use physics, mechanistic understanding of particles and their behavior and mathematical models of that, and epidemic models to try and understand what's happening. And no one thing gives us the answer. And even when we have got an answer, we know it's uncertain. And I think what we've learned already is that we do know that inhalation is probably the dominant factor. We do know that being close to somebody is a dominant factor, but we know that there are multiple routes of transmission and different risk factors. And we also know that not everything is immediately what it seems. It's very easy to say, oh, look, there's an outbreak in a workplace because lots of people in this workplace have COVID. Actually, quite often it turns out that it's not the workplace, it's the fact that they travel together, that they interact socially together. So the workplace facilitates, but is not necessarily the cause. And we have to be really careful with that. If we look at what we've learned about risk factors, we've learned that it's a combination of human and environmental. And from a building services perspective, we can manage the environmental much more readily than we can manage the human side. So although there are things we can do from a building's perspective, it's not as easy. So human factors, we do know that, you know, if you're more active, so particularly aerobic activity, if you breathe higher, if you're singing, that's a big risk factor. We know the longer you're there, the more likely you are to be exposed. We know that people who interact more readily, have more frequent contacts, are just at a greater risk of exposure than those who don't interact and are much more isolated. We know that people's own behaviours, whether they wear a mask, whether they perform good hand hygiene, matter. And then we know that socioeconomic factors play an enormous role in this. This is not an equal disease by any means, and we'll come on to that a little bit more later. But then from an environment perspective, and I think this is where our buildings really come into it, where we've got higher occupant densities, where we've got poor ventilation, where we've got spaces where people are sharing lots of surfaces, lots of spaces together, and where temperature and humidity are poorly managed. All of those give us higher risk locations. So our buildings set the conditions, they enable us to interact, but they can't manage all the behavioural factors. And it's really important to bear that in mind. You know, you can have a very well designed building with very good ventilation. You can still have an outbreak in there if people interact in a way that creates that outbreak. None of this is new though. So we've learned a lot this year, but we only have to go back in time. We can go back into the 1800s and we can find that we knew a lot of this already. And Florence Nightingale, one of the pioneers of this, pioneers of statistics, of disease, understanding transmission, really kind of set out essentially what we still know: space your beds out, have high ceilings, good ventilation, natural light, opening windows, etc. And she just advocated all of the things that essentially make a building good. And if you make a building good, you reduce the disease risk as well as manage many other things too. I found this one quite fascinating. This was from a report in 1905 on the House of Commons and concerns around ventilation and infection transmission. And they found that when the debating chamber is in use, they get more bacteria in the air. I guess there's people talking quite a lot and spitting that bacteria into the air. And they associated that with upper respiratory passages. And this is quite a fascinating report to look at how they considered the ventilation design in the House of Commons. Really interesting as well is that they also at the same time were concerned about microorganisms on people's feet brought in from the streets, because of course at the time there was rather a lot of horse muck on the streets. So it tells us how some times have changed. And I think, you know, if we start thinking about how we understand disease transmission, we've been looking at this for a long time. It's not a new phenomena. And I think one of the reasons we have been looking for a long time is it's hard. So these give you 3 examples through history. The one on the left was a seminal study to look at TB transmission. TB was originally thought to be droplet close range transmission. People worried about surfaces, people worried about spitting. Actually, the work of William Wells from Harvard and his colleague Richard Riley demonstrated it was airborne, and they demonstrated it by taking the air from a TB ward, they passed it through ventilation ducts, they passed it through a cage of guinea pigs, and the guinea pigs got TB. And at the same time, they also put ultraviolet lamps in there and demonstrated that ultraviolet disinfection could reduce the numbers of guinea pigs that were infected. Okay, that's TB, and we do know TB is an airborne disease. It's a long-range airborne disease. The study in the middle is a repeat of that seminal study by Wells and Riley, done by Rod Escom in the early 2000s in Peru. What you can see there is guinea pig houses on the top of a roof of a TB hospital, and it showed the same thing, but what it was able to do is now we have molecular techniques to be able to relate which patient infected which guinea pig, and to be able to identify that some patients are super spreaders and the majority don't transmit very much, but a small number transmit a lot. And then on the far right is influenza, and this was a human challenge study where we were trying to identify whether influenza was transmitted through contact and droplets or through aerosols. And it was a huge study, it was a complex study, and it was not able to distinguish because we didn't get enough transmission. And that, you know, it's a disappointment, but actually that shows how hard it is. Actually understanding which are the dominant modes of transmission for many things is really challenging, and we can't just magic an answer. Look at ventilation. Look at how ventilation's changed over the years. It's quite interesting, and I know this is not a complete timeline. There are other numbers in here, there are other studies in here, but to just flag how we've shifted our thinking over time. If we go back to the very beginning, Treadgold was one of the first people to calculate a ventilation rate. He reckoned it was 2 litres per second per person based on human metabolic needs. We then get a shoot up, right up into It's actually 30 cubic feet per minute, or 14 litres per second per person, driven by physicians worried about transmission of disease. But then, of course, as we learn more about treatment of disease, we start to worry about comfort, we start to understand about energy, we start to design ventilation systems that can recirculate the air. These numbers come down. So they come down to around 5 litres per second per person. We settle in about 1946 on a value of about 7.5 litres per second per person. And most of these are from the US. We drop it back down again in the 1970s when we worry about energy. And then we go back up again in the 1980s, again, because we recognise people were smoking in environments. And then we've settled really for probably a good 20, 30 years on about 8 to 10 litres per second per person, based around a balance of comfort, contaminants and energy, but not really thinking about disease. Only in hospitals we think about that. I've noted a study there by Jan Sundell and colleagues of Systematic Review from 2011, which suggested maybe we need higher, 25 litres per second per person for health. Put a question mark at the end, what do we need now? I really do not know the answer to that. I wish I did. I wish I could say. I suspect it's a bit higher than we have now, certainly if we want to manage disease, but it's very hard to say what that should be. But we do need to think about how we balance disease in there with other factors. And if you look at this, really there's not very many points in history where disease has influenced this significantly. So something to think about, you know, buildings are for people, they're not for the building itself and for the energy use, it's for the people who are in them. So over the past year, what have we done? We've had a very rapid response. Organisations, individuals have worked their socks off. We've changed things in workplaces, we've changed occupancy, we've changed layouts, we've changed work patterns, we've changed ventilation, we've changed our behavioural measures. These have all been, you know, the response has been fantastic. Nearly everybody has delivered something successfully. It's a bit of a sticking plaster though, so it is an immediate response to a crisis. And we can't, it's not a sustainable response. We can't just open the windows forever and hope for the best. We have to now start to think about how do we design this in properly? How do we solve this long term? But there are still questions there. There are a lot of good questions, a lot of big questions. Many buildings, we don't actually know what the ventilation rates are. We don't know how to measure it successfully. And we don't know how to, you know, how do we know how that varies in many environments? We also don't know what the metrics we need are to give us the right, you know, what are the performance metrics we should be looking for, and how do we balance those, say, for infection versus air quality versus energy? And then how do we link our ventilation to behaviour? So it's very easy to think of a building as a technical solution, but it's not. It's actually influenced very heavily by human behaviour and how people interact with it. And we know that this matters well beyond COVID. So reports on the impact of air pollution from a few years ago now really highlights all of the different exposures that we experience in our daily lives. And the fact that we really need to consider this, you know, it's not just about disease, it's about our exposures in the environments that we live and work in. And we're struggling though, it's not a straightforward solution. There's a whole raft of competing priorities. Many of you will be very well familiar with these and recognise that, you know, there's not a simple, easy answer to this. And we do need to think holistically about how we capture all of these different priorities, barriers and opportunities together to try and understand how we improve our environments. And we need to recognise this is really complex. You know, it's very easy to say buildings should do X, you know, buildings should have, we should have a standard for air quality in buildings. Yes, we should, it'd be great, have a sticker on the door. But actually getting to that is challenging. We can't do it overnight and we have to think through the process of doing it. And it's a complex environment, it's a complex system where we've got the physics of that environment, how the building interacts with the indoor environment, the outdoor environment, the people within that space, but how all of that is driven by regulation, legislation, guidance, standards, and our education and cultural norms, how our behaviour influences all of that. But ultimately, all of that determines many of our health outcomes and many of our energy outcomes. So we really need to think through this whole complexity of the system. And I mentioned earlier inequalities. We know that not just COVID, but also air quality, the impacts amongst the groups who are the most disadvantaged. And that means we've got influences around geography, the housing people are in, the jobs, their income, the fact that those who live in the poorest areas tend to also be the people who have to use public transport. We also know that there are issues with levels of education and the underlying health that make people more or less susceptible to things. So whatever we do, we have to think about these inequalities and make sure that as we adapt our built environment, that we level up, we consider how we can more equally create a society and our built environment that's more equal for people. I think it wouldn't be right to not mention the issues around capability and capacity. Again, many people here will be very well aware of these, and particularly the Hackett report. Now, I know the Hackett report focused on fire safety and focused on how we delivered our built environments and the quality of our built environments for fire safety. But actually, I think there are systemic problems that go into how we ensure we've got good indoor environments in our buildings. We've got standards, we've got regulations, but we know that huge numbers of buildings do not comply with those, that we've got poor environments, we've got multiple buildings with no designed in ventilation at all. Some of that was never designed in from the beginning. Some of it was it's been created because people have chopped up spaces and reimagined spaces and delivered that ineffectively. We also know there are multiple issues with technology. You know, MVHR systems are a great idea, but we know that they don't always work in practice. We know that the filters are hard to change. We know that people don't understand them. They switch them off. They're noisy. They're badly installed. And we need to tackle that. We need to tackle the interaction between the technology solutions and skills and training to deliver it properly. I think we also get unintended consequences. We're very have a tendency to think about a single problem, carbon or energy or insulation, but we don't think about the whole thing holistically. And we've got to now think buildings holistically rather than deliver one solution to one problem. So we need to make the case for better buildings. We know they improve health. We know they improve sleep, productivity, performance, well-being and respiratory symptoms. We know that it can change productivity. 9% is nearly half a day a week. If you get your air quality right, that's a lot of people who are maybe less productive than they should be. We know that the ONS estimate 5 million days a year lost due to respiratory infections. And if you go back to 1997, you can get data from the US which estimate that we'd gain annual gains from better air quality would be over $40 million. It's not new. Why are we not doing this? We should be thinking about this already. Short term, we're going to have to do some things. We're going to have to do some things in the next year to 3 years. And we're not going to just be able to magic amazing new systems in every building. So we need to think about building awareness, recognizing what's needed. We need that risk-based approach to allow us to balance the safety issues around infection with energy. We need to make sure that we've got good baseline actions. We need to bring up the quality of maintenance. We need to think about technology. What can we use quickly, but use it appropriately, the right technology in the right places. And we need to start thinking about how we train and educate to deliver now and to plan what we need in the future. We have got a lot of gaps. We've got a lot of gaps around COVID, and this is a huge study called the PROTECT study led by Health and Safety Executive that's bringing together people across multiple different research areas, looking to bring together human behaviour, virus characteristics and details and environment to try and understand that complexity of transmission and what that means for how we mitigate our environments, both in the short term and the long term. And we also need to think about how we think more broadly around air quality. We have a research network which looks at this and thinks about how we couple together indoor and outdoor flows, how we might be able to come to a new position around health-centered ventilation design. So just to finish, I think this is a point where we need a shift, where we need to think about our buildings differently. I said before, buildings are for people. We shouldn't be designing our buildings where the key metric is around how does the physical asset perform. It needs to be embedded. The health metrics need to be embedded with sustainability metrics. We need to have human-centered design, not just building-centered design. We need to think really holistically about how we interact indoors and outdoors together, thinking about how we design out the inequalities in the process, and how we connect all the way through for design and regulatory. And we need to recognise it's not easy. We're not going to solve this overnight. We need lots of input to this together to solve it. And there will be mistakes on the way, and we will not have perfection, but we need to try and all move into a position for better buildings. And I think it's really important we try and make that case for better buildings. You know, thinking about many organisations, what would you like to invest in next year? Are you going to invest in some nice flashy digital tech that will allow you to do hybrid working? It'll look great on your website. Or will you invest in better ventilation, which won't look great on your website, but will actually make the environment better for people? You can see how it's easier to make a case for the digital tech because it's more snazzy. It makes you look more forward thinking. The other thing's backlog maintenance. And, you know, really, but we need to prioritise that. And we need to now think all the way through the process from policymakers through to design, to training, to education, to delivery, to how we actually build our capabilities and capacities to have the buildings that we really ought to have in our country. And I'm going to say thank you very much and stop there.
Thank you very much, Kath. That's been a really helpful whistle-stop tour. I've got several questions popping up and we've got 3 minutes. I'm going to start off by asking if you could answer very briefly. There's a question about why transmission is worse in winter, and is it related to relative humidity?
That's a good question. I think it relates to a number of factors. One might be relative humidity, because the virus does favour, it likes lower humidity and lower temperature environments. I think it also is that people tend to spend more time indoors in the winter, are more likely to close the windows, and are more likely to interact in an indoor space. So I think there's 2 factors in there.
Thanks, Kath. A slightly more tricky one. You've said we need to improve our buildings, and the questioner asks, how can we improve buildings in the age of value engineering, or perhaps what's sometimes called vandal engineering?
That is a very good question, and I think it's the same question around carbon and energy and sustainability too, in that we need it in the life cycle cost, and we need to start thinking about whole life cost rather than just the operational cost or the capital cost. And we need actually to quantify the health effects. We need to put metrics to it. You know, I mean, if you've got a workforce that have, you know, even a 2 or 3% reduction in productivity because their building's poor, and it's a high, you know, there's 1,000 people in your workforce, you can see that's going to rapidly dominate over your energy bills in terms of their, you know, their wage bills. So, you know, we do need to think about how we quantify this economically to then make the case for why we need to tackle the indoor environment and the sustainability together at the same time. You cannot have a net zero building that is a sealed building with no ventilation. It's a fail.
Thanks, Kath. That rather leads on to what I'm going to have to take as the last question because of time. One of our participants has asked for the reference to your 9% productivity and IAQ.
Oh,
and I guess that's an important reference, even if you can't remember it off the top of your head, because that's the kind of thing that feeds into the value engineering issue.
Yes, it's a Danish study, I think, by David Wyon from a few years ago now. And they estimated it was 6 to 9% productivity reduction because of poor indoor air quality.
Right.
I picked the 9% because statistics.
Well, but it makes the point that there are significant gains here if we take the holistic view, which we tend not to do in value engineering. I'm really mindful of time. I know that Kath has to go to another commitment. I'd just like to say on behalf of everybody, thank you so much for taking the time to prepare this and to present to us. It is very much an evolving area, and there may be more on some of these things even in the next few days. So thanks very much, Kath. It's not easy to do the routine round of applause in a Zoom meeting, but perhaps I could ask you to imagine that you're now getting a thorough round of applause, and thanks ever so much.
Thank you, it's been a pleasure. Thank you very much.
To delegates, I just need to say that your CPD code for the session is 4159, and to ask everybody else if you can log off and then log into the next session, please, and we look forward to seeing you there shortly. Thanks very much.